So for covalent compounds, it's important to know a definition called the Octet Rule. So in covalent compounds, atoms want to have a full set of valence electrons. So in the case of something like sodium, we look it up and it's in group 1A, and we know that we have one valence electron. So what does it mean then it wants to have a full set of valence electrons? Well, doesn't that mean then that sodium would want to gain 7 electrons in order to become stable? Well, we know from dealing with our electron orbital diagrams that our electron configurations as well, that the last orbital for sodium is the 3s. And we know that there's 1 electron in the 3s. And we know that the 2 orbital is completely full. So if sodium were to get rid of this electron, this would now be the valence shell. This would be the outer shell. And it is completely full. So that's why sodium wants to get rid of it. Similarly with chlorine, in its valence shell, the outer shell in the n equals 3, this one essentially has 7 electrons sitting in it. There's 7 electrons around it. So what it would like to do is gain an electron and actually have a full set of 8 electrons in the shell. So in the 3s, it would like to have 2. In the 3p's, each of them, it would like to have 2 electrons as well. That's where the 8 comes from. So that is where the octet meaning 8, that's where the rule comes from. So again, in the case of something like chlorine, chlorine only has 7 valence electrons. It would like to gain an electron in order to actually have a full octet. But it doesn't have to just steal an electron, say from sodium. It can share an electron. So let's say, for example, I have another chlorine atom around. So I've got 2, 4, 6 electrons, plus this one is 7 electrons. But if I were to share these electrons, I now have another set of electrons that chlorine can have around it. This electron right here actually becomes part of this chlorine atom. So now I have 2, 4, 6, 8 electrons sitting around this chlorine, and it's happy. And the same thing goes for this chlorine. 2, 4, 6, and now I have 8 electrons from this bond. They're sharing the electrons, so this chlorine is happy. Both of them have full octets. Both of them have 8 electrons around the molecule, around each atom, sorry, and they're stable octet. And I can redraw this molecule as this, with this line representing the shared electrons. It's the same thing as this, it's just a straight line. So atoms in covalent bonds typically try to do a couple of things. One, they try to obtain an octet of electrons around them, and this is so that their valence shell is full. And this is typically seen between non-metal elements with a covalent bond. And we can see this in an orbital diagram with chlorine. Chlorine has 17 valence electrons. We know that in its outer shell, it's the n equals 3 is the outer shell. All of these electrons contribute to the valence electrons. So chlorine has 2, 4, 6, 7. So we can redraw chlorine as this, and that's why we put those dots around it. It represents the outermost electrons. So now we can clearly see that it wants 1 electron, and if it were to obtain it, we would fill in the extra dot over here, and that represents the same thing. We've now got a full shell. This is 8 electrons now in the outer shell. There's 8 electrons here. There's 8 electrons total in this entire n equals 3 shell. And so this is a stable octet. Now there is one atom that can't achieve 8 electrons around it, but we still use the term octet, and that would be hydrogen. If we look up hydrogen on the periodic table, it only has 1 electron, 1 proton, therefore 1 electron. If we were to fill in the orbital diagram, there is a 1s, there's only 1 electron. So in order to fulfill the entire 1s orbital to be filled in, it needs to gain 1 electron. Now, it can only have a maximum of 2 electrons in the n equals 1 orbital. So we are going to fulfill the octet if we fill in and give it 1 more electron, but we've only got 2 electrons, yet we still call this the octet rule. So they probably could use a better name for it, but that's the way it goes. So if we were to represent it like this, and now I have another hydrogen over here, I can share these electrons, and that means that, here, let's do this in different colors. I'm going to have this electron is red, and the hydrogen is red, and so now for this hydrogen atom, if I were to fill in its octet, I now got the extra electron. This has 2 electrons, the n equals 1 is full, and therefore this is a stable octet, even though it only has 2 electrons in its shell. And so that is applied to this atom. If we go to this atom, the same thing would apply. The hydrogen only has 1 electron. We're now sharing an electron with this atom, so its shell would end up with 2 electrons, and so this atom would also be stable. This atom is happy, this atom is happy. We have a stable octet around each one of the atoms, and therefore this molecule would exist